Pop culture loves to paint black holes as cosmic vacuum cleaners, wandering through space and indiscriminately swallowing every star, planet, and spaceship in their path. The truth is much less chaotic. A black hole is simply a localized gravitational body. If we were to suddenly swap out our sun for a black hole of the exact same mass, the Earth's stable circular orbit wouldn't change at all. We wouldn't suddenly spiral inward. Because the mass hasn't changed, the gravitational pull remains identical. Earth would keep flying right along its usual path. The only real physical consequence is that we would freeze in the dark, completely cut off from the light and heat the sun provided. This thought experiment shows that black holes obey strict, predictable laws of gravity. They are standard celestial objects that happen to be incredibly dense. To get something that dense, you need a massive star to run completely out of its internal nuclear fuel. For millions of years, that nuclear burning creates an outward pressure that perfectly balances the inward crush of the star's own enormous gravity. When the fuel runs dry, gravity wins. The star collapses inward, resulting in a violent supernova explosion that blasts the outer layers into space and compresses the remaining mass into an impossibly tiny, massive point. These common stellar black holes are usually a few times heavier than our sun, but scaling up, we find giants containing millions or even billions of solar masses. One of those supermassive giants, named Sagittarius A star, sits directly at the center of our Milky Way. Its massive gravitational pull influences the motion of billions of stars, and scientists believe it may even direct how the entire galaxy forms and evolves. Because these objects anchor the very structure of our universe, we have to look closer. To truly understand their mechanics, we have to stop observing them from a safe distance and imagine what happens when we physically descend into one. The obvious problem with observing black holes is that they do not emit any visual light. Traditional telescopes are completely useless when searching for dark objects against the dark backdrop of space. Astronomers work around this by looking for the effects of gravity instead. When glowing gas and dust are pulled toward a black hole, the material compresses, creating immense friction and heat. That superheated material forms a bright, glowing ring that outlines the dark silhouette inside. This image, captured in 2019 in the galaxy M87, shows exactly that. We are looking at a bright, asymmetric ring of superheated gas swirling around a completely dark center. That glowing boundary perfectly matches the mathematical predictions of general relativity. Decades before we captured this photograph, Albert Einstein's equations mapped out precisely how massive objects bend space and time to create this exact visual signature. To see those extreme distortions of space and time in action, imagine an astronaut flying a capsule directly toward that dark center. To an outside observer, gravity stretches the astronaut's light, their movement slow to a crawl, appearing totally frozen. But the astronaut notices no delay. Time flows normally for them, taking 1 second per second, entirely unaware of the observer's illusion. Physically, however, the descent is brutal. As they get closer, the gravitational pull on their feet becomes significantly stronger than the pull on their head. This extreme difference vertically stretches their body in a process physicists appropriately call spaghettification. The astronaut eventually reaches the event horizon. This is a strict mathematical boundary. To cross back out, you would need to travel faster than the absolute speed of light, which physics dictates is impossible. Crossing that invisible threshold means dropping out of the observable universe entirely. It permanently severs all communication and physical causality with the outside world. Below the event horizon lies the singularity. This is a specific point in space where all of that enormous stellar mass has been compressed into infinite density. At infinite density, our mathematical models fail. Gravity becomes infinitely strong, and the standard laws of physics and spacetime stop working. This leads to a severe conflict. The rules of gravity state that matter falling in is completely crushed. However, quantum mechanics dictates that the fundamental information of the universe, the unique physical properties of that matter, cannot be permanently deleted. This contradiction between gravity and quantum mechanics marks the exact point where our current understanding of the universe stops working. Physicist Stephen Hawking challenged the assumption of total darkness when he proposed that black holes actually leak microscopic amounts of energy. Over immense stretches of time, this slow energy leak, now called Hawking radiation, causes the mass to deplete. Wait trillions of years and a black hole will completely evaporate into nothing. The extreme space-time distortions surrounding these objects even leave the door open for theoretical wormholes, bridges connecting distant regions of space or entirely separate universes. These objects act as the ultimate physical stress test, forcing us to reconcile conflicting laws until we find a way to explain the universe.